So good afternoon everyone. We'll wait for 2 more minutes. Am I audible? So in the last class, what we have done is how to smoothen the profile by using a drop and increasing the pipe size. Then how to set up SES parameter for the catchments. So this is what we have done in the last class. So in the today's class, what we're going to see is like just one small recap until what we have done, then how to set parameter for swim method, then outfall structure and connections, and profiling is how to do smooth and profile, because the stormwater, in the design of stormwater, making a smooth profile is more important. That's why I'm making it more important in the every class. So this is what we have done, and pending things in the COGEMs. So basically, to set up a normal stormwater network design, first we need to set up design constraint, then conduit catalog and inlet catalog. Then we need to set up scenarios, alternatives, and options for rational and dynamic method. Then after that, we need to give parameters for catchments. If you are running in rational, we need to give time of concentration and runoff coefficient. And if it is in SES runoff method, we need to set up a runoff method as a unit hydrograph, like this. If you go to catchments, here unit hydrograph method will be available. So for the SES runoff method, you need to set up this. So the things which is needed for unit hydrograph is CN curve number and time of concentration. So the CN curve number will be taken from the standards, and time of concentration also taken from the standards, which they have mentioned is 10 minutes only. So these are the two parameters needed for this runoff method. After that, we need to give rainfall inputs like time intensity or time depth. Then we, after running the model, we need to do a profile smoothing. If it is if the pipes are not if the pipes are not enough, we need to increase the pipe size and make a drop whatever the place we needed. After that, we need to validate and stimulate the error. This is what we have done. The pending things are like swim runoff method parameters and outfall and the structures, then control sets like after this level we need to model have to operate after this certain control levels are there, so that after that COGMs will be over. So let's start the class with the swim runoff parameter. So basically, what is the difference between SCS and swim runoff method is in the SCS runoff method we will be using total runoff. So whatever the runoff is applying will be whatever runoff we are giving, it will be directly applying to this catchment. In the SCS runoff method, effective runoff method will be taken because I will show that. If you go to this, select the catchment table, go to runoff. So before that, create a different scenario for swim method. Go to scenarios, which is in the home tab, scenario, rational, new, make a child scenario for this swim runoff method. Select this. So we will be working on this swim runoff method because we have make this make us current. So after that, go to this. So in this area, I just want to mention one thing. So what are the changes we are doing in the swim runoff method, because we have make it as a child now. So there will be, it won't affect the rationals and SCS which we have created previously. So what are the things we are changing in the rational method is as a base scenario, that will be changes in this child scenarios. So go to the swim runoff method, select the catchment, edit group, catchment table. So change the runoff method to EPA swim runoff method. So for the every runoff method, different types of parameters are needed. For the EPA swim runoff method, if you go to click any catchment, before that we need to change in the options. We need to set up some things in the scenarios which you have told in the last class itself. So basically the things need to be changed when you are doing in the dynamic is active topology, boundary condition, hydrology, and the rainfall runoff. So these are things majorly we need to change when we are changing into the dynamic condition, which after that we are creating a child scenario. So for the active topology we need to create one swim, for the boundary condition we need to create one swim, and for the hydrology we need to create one swim. So for that, go to alternatives, for the rational, new, child, swim. The purpose of creating this is the things which you are changing in the dynamic method, it should not replicate in the rational, because rational which you are doing only for the pipe sizing and the pipe parameters. So physical need to be same, because what are the things which you are changing in the rational, it should be the same. So after that, the boundary condition, go to this child, swim. So for the rainfall, there is no need to create a child, because it is a single thing only. So we can create a base itself. So 5A24. So after creating the alternatives, go to the options. So we have set up everything. Only thing is we need to add it in the scenario. Go to swim scenario, active topology, change to swim, boundary condition, change to swim, hydrology, change to swim, then rainfall runoff, change to swim, then the solver. The main thing is solver. You need to change to swim. So for this we didn't do anything. So go to options, select this option, change to explicit, swim solver. So here we can set up the time until how much it can run. So duration we have set up to 24 hours. Then output incremental will be 5. So that's it. Now click on this. So after changing the runoff method to ePassWim, these are the parameters we need to be filled. Okay. So these are the parameters like characteristic width, storage, impervious depression, storage pervious depression, storage depression pattern. So what is characteristic width? Characteristic width is nothing but it's kind of a sheet flow. So consider this as one road. We have splitted this into multiple catchments. Okay. So water is flowing like this. So characteristic width is nothing but how much width the flow is happening. So this width is there now. So we need to mention this width into in that area. So how to get this characteristic width? When you go to the catchment, it is like a similar kind of road only in all places. So there are two ways to do this. There are three ways to do this. One is through cross section. So that will be the perfect way. So in that for every roads they have mentioned the width. So another way is like it's a kind of approximate way only. So first select the roads. So if you so consider this as one road. Go to measure. Just measure the width from this to this. So it's like kind of 6.2. So basically what we're going to do is for the whole roads we will be giving 6.2 as a characteristic width. So one thing is through cross section, second thing is through measuring directly, third thing is through GIS. So the GIS will be we can able to make the area and perimeter. So from that we can create a formula and get the width, but that will be not too accurate. It will be like for for a sample model we can do in that, but better way to do is through cross section and measuring directly with the in the model. Okay. So the second thing is storage impervious depression, storage pervious depression. This will be in the guidelines itself. So it's a kind of if you consider this as a road, we have split it into catchments. In that so in this road, all 100 percentage won't be impervious. Maybe some area may be into green space. So otherwise there will be some median like a small area into green space. So in the swim method we have options like we can split this green area from the road option from the impervious area. So if you are taking this whole thing as an impervious area, it will give more runoff. But if you consider this green area into your catchment parameter, so some runoff will be less. So we can reduce the pipe size and we can reduce the storage whatever we needed. So for the accurate measurement, we'll be using 90 percentage as impervious, and the small area will be considered as a 10 percentage as pervious. So for that, for this, we'll be giving separate values. So for that only they are given like storage impervious, storage pervious depression. It's a kind of how much depression, how much storage will be happening through while happening in the flood. So in the manual, in the standards they are given like 2.54 in for the impervious depression, and the pervious depression it will be like 7 point something values. Another thing is Manningson. So I have told like this now. So 90% area will be impervious, 10% area will be pervious. So for this we'll be giving Manningson. So for that only we need to separately give into Manningson. Then the percent impervious. So in that 10 percentage, how much percentage will be impervious we need to mention. Like it will be like 90 percentage, 100 percentage. So in that 10 percentage also we can differentiate how much percentage impervious we can give. No, sorry, I am mistakenly there. So in this area only we can give like how much percentage need to be impervious. So in the roads will be giving 90 percentage. So it will automatically consider the remaining 10 percentage will be pervious area. So slope we need to mention based on the cross slope. So based on the cross slope we need to mention the slope. It will be basically based on the grading file only. Then percent impervious zero storage. This thing only like in the out of percent impervious zero storage. So this will be like how much percentage storage is happening while the runoff is taking. So in that we'll be doing for a worst case condition only. So we'll be directly giving 100 percentage here. So percentage router is 100 percentage of water which is falling into the catchment, it will be routed into the gullies. Then sub area routing. So in this we'll be having some multiple options. If you click this, if you go to sub area routing, we'll be having both to outlet, impervious to pervious, pervious to pervious. What this means? Says what is both to outlet? Both to outlet is it's kind of, if you consider this road, the water falling into this area will be directly connected to the gully. So this condition is both to outlet. Okay, impervious to pervious. If some area of if you consider this area is kind of impervious area and this area is kind of pervious area. So the water is flow from impervious area, like two areas are there. So gullies will be placed here. This will be impervious, this will be pervious. So usually how the water will flows is it will come to the curb and it will directly to the gully. So in this area if it comes like this and direct to the gully means we can mention this one, impervious to pervious. It's like samely to the pervious to pervious also. But in the new guidelines they have mentioned like for the plots we will be using SES runoff method. For the roads we will be using this e-passing runoff method, because it is difficult to find the plot area plot characteristic width, because plots will be in the different shapes, nah? So it is difficult to find, so they automatically change maybe due to that approximity. After that we will be lost in the loss method, we will be using SCSCN method. Then for that we will be mentioning some values. Then drying time days, this is based on most probably we don't use this drying time because we will be running for one day or 2 day. So drying time is a kind of time for fully saturated soil to completely dry. So how much time it takes to dry, so in that we need to mention the days. After that infiltration pattern need to be fixed. So this is how we need to fix the uh, parameters. So first we will fix this. Okay, before fixing we need to set up everything in this attribute table, like what are the things in the runoff we will be adding to the attribute table. Go to this, right click, edit, catchment tables. First we need to add is characteristic width, like edit, search for characteristic width. Second is storage impervious depression. Third is Manningson impervious. Manningson pervious. Fourth is percent impervious. Then slope. Percent impervious, zero storage. Percent routed. Loss method. Then that's it. So the characteristic which we have seen is 6.2. So this will be like okay, as of now I will be putting 2.54. This will be 7.5. So Manningson we need to give 3. So these things we need to be put based on the guidelines only. For the class purpose I will be putting something approximately. Percent impervious. So we need to consider, we are considering 90% as impervious and 10% as pervious. Slope, just put here there will be no zero storage, 100% will be routed. So here both dotted. Okay, the curve number which we are going to fix is, so usually 98 for roads, so we'll be fixing 98. So previously I told like for the roads we'll be using swim runoff method. For the SCS we'll be using swim runoff method. So we have almost fixed everything for the swim method. So one more thing we need to add is rainfall to this area. Go to rainfall runoff, which we already created here. And depth we'll be using. So go to alternatives, swim. Here select the runoff which we have created in the last class. So now the parameters are set for the swim method. This is how we need to fix for swim runoff method. Okay. Okay. So now what we are going to do is for the plots we will be fixing SCS runoff method, and the swim we will be fixing swim runoff method. So how to do that? Just create just from this create one child, swim plus SCS. make us current. So in this area selection set will be more useful, so which we have already created in the first class itself. Select the plots, go to edit, group, catchments, select the runoff, click to unit diagraph. So here what we need is SCS core number and time of concentration. So the plot they have already mentioned like 75 will be using for this plot. Okay, this is how we need to fix for SCS. So time of concentration remains the same 10. Now in this scenario what we have done is for the plots we have fixed to SCS runoff method, we can see it here, and the rows we have fixed to swim runoff method. So this is the effective runoff method we will be using in this model. So we will with the free outfall we will be running this. First validate it. So there is no warning. Then run it. So any doubts in setting parameters for the catchments? So our model is almost run. So go to report, node flooding summary, check whether there is flooding is happening or not. We can see manual 3 is flooding and there is some surface flooding. Surface flooding can be avoided because we are using inside gullies, so there will be some surface flooding for some period of time is happening. So this is the period of time. So how much time we can see 24 hours there is surface flooding. That is quite wrong. We'll fix it now. So this is the flood volume 0.012 in the manual 3. So we need to reduce this flood. So before reducing the flood and profile adjustment, I would like to finish this outfall structures. So outfall thing. If you click to the outfall, if you considered what are the outfalls needed is first will be free outfall, which is there is no condition for that. So what are the flow coming from the pipe, it will be going out. So another thing is a normal outfall and user defined tailwater condition. So these two things will be same only, but in the normal outfall we don't be giving any value specifically, but in the user defined outfall user defined tailwater condition will be giving certain values. Then tidal outfall is like if you are connecting the outfall pipe to the like a ocean or beach kind of thing, there will be some backflow will be there. So based on the tidal outfall only we need to fix that value. Then the boundary condition is to fix it's this the boundary condition is mainly used to connect to the structures like pond, tanks, in soakaways. So what are the flow coming out from the outfall? It will be directly connected to the tank. So first we have seen the free outfall. Second we will be going to see the normal outfall. So normal outfall is a kind of thing we can see it here. After a certain period of time, there will be some uniform flow will be there. So based on that some depth will be there. So that depth we need to measure it and we need to give it the direct, we need to mention that in the normal outfall. So how to give this normal outfall in the model? So go to COGEMS. So as fixed, we have created a separate boundary condition here. For the swim, we have created a separate boundary condition, so it won't affect in the boundary condition the raster. You need to ensure that. After that, click the outfall, go to boundary condition type, it will be here, select the normal outfall. So this route to catchment is like if you are connecting something to the pond, consider this as one pipe. If you are connecting something like to the pond or culvert or something, anything stagnant water will be there, na? If you are giving some normal depth of 0.5 meter, okay, if the water exceeds to 0.7 means some amount of water will be backflow will be happening. So if some manual is already surcharge condition, so through the manual there will be some surface flooding will be there. So for that we need to select the catchment. So for that purpose only here they are given route to catchment option. So click on this, click the previous catchment. So there will be some surface flooding in the catchment. After some time it will be, after some time, so that water will enter the system and get into the outfall. So this is the normal condition. Then the tail water condition. So this will be most commonly used when we are connecting to the existing manual. Okay. So consider this as our proposed manuals, proposed pipes, with some manuals. You are connecting these to some one system which is coming this side. You are connecting to the existing system. Okay, here there will be one manual. If you are connecting now, so already this system will be filled. So this system will be filled. There is no water to escape from our system. So there will be no water will be escaping. So it will be filled here itself. So there will be some backflow will be happening. So in that surcharge also will be happening in the previous manual, like to ensure no flooding, we need to decide in that way only. So after the hydraulic gradient, like this flow, after this flow comes, reduces only. Consider this as 500 pipe. Okay. Already this is fill. So there is no water to escape. After some time, after the period of like after the peak, if the peak is happening in the 12th hour, so after the peak there will be some amount of water will be like half filled pipe only will be coming. So the water will be flowing from like this only. So half filled water will be flowing. We will be having some space now. So in that time only our system will release the water inside this. So in that condition we need to ensure this tail water condition. So based on the pipe size we need to give the level where we are connecting. So after the hydraulic gradient reduces, so our water, so after the hydraulic gradient reduces, the water will be discharged from our system to the existing system. So to avoid the negative flow into our system, we need to ensure that we are providing flap gate in this pipe. So if you click this pipe, it will ask for a flap gate. So we need to give true. Whenever we are giving a normal depth, user defined or title condition, we need to give this flap gate should be true. Okay. So then only there will be no water will be coming. So if this system is already filled means some amount of water may come inside now. So to avoid this entering only, we are giving that flap gate. So there will be no water will be coming inside, only it will be stored here. And our own water will be surcharged. After some time, that too will be discharged into this existing system. Okay, so this is we have finished free outfall, normal, user defined. Then we will be moving to the boundary condition. So boundary condition is like, go to layout, uh, create some pond, right click, done. We need to give whatever the water coming from this outfall will be directly, whatever the water coming from our system need to be filled in this pond. So in that case we need to use this boundary condition. Double click, go to boundary condition, boundary condition type, set the boundary element. In the boundary element, select the boundary element, so click this. Okay, so now if you run the model, the water coming from this system will be discharged to the system, discharged to the boundary condition. Okay, so before that we need to fix this pond. Some rough value will be putting now. We are going to develop a rectangular pond. Okay, so 0, it will be 100 meter square. For the 25 meter, it will be 100 meter square. Make the pond little bit here. First see the profile. So this is for the previous profile until the outfall. So we'll be adding a tank here. So pond here, pond or tank both are same only. Select this manual, starting manual, end with this pond, open. So we have given some random value to 0 now. So because of the pond is created until here, so we need to fix it to 35, 35 to 37 we can fix it. So whenever we are entering values, it should be in the ascending order only. So we should not give like 37 to 35. It should be like 35, 37 or 39, 100. So we created in the upside. Okay. So the value should be here 32. So we are creating a 2 meter pond with 100 meter square. You understand this now? So 34 and 37 means we'll be creating one pond like this into 100, 0 to 100. So the depth will be 2 meter. So 2 into 100 will be 200 meter square area. See, we have created a pond here, PON. If you run means some amount of water will be stored in the pond. See, the pond is getting flooded, so this pond size is not enough. So based on the volume we need to create the pond size. Before that we need to ensure the area availability for the pond, because in many site conditions there will be no space for the pond or tank which we are creating. So we need to ensure that area availability. So based on that we can increase the depth or increase the area we need to decide. After that we need to finalize the pond size. So this is how we need to create. Yes.
Hello.
Ah.
When is that elevation and area table window you were showing? Can you please show it again?
No, your voice is not clear. Can you tell once? Hello, Surya.
Hello.
Ah, yeah. Tell. Can you tell once?
That elevation and area table window you were showing now. Can you
Ah.
please show it again
Yeah. Okay. Okay. So
for the pond?
if you click on the pond, you can go to the physical. In the volume type, we can create elevation area. There will be multiple options. So better to create with elevation area.
Sorry.
In the If you click on the pond, go to physical. In that the
Okay.
volume type will be there. So in that we need to select the elevation area. Okay. So after that, go to the elevation area, click this, so the table will be coming like this. So in this we can enter the values.
No. In this table,
Ah,
elevation means top water level, right?
elevation is like not top water level. This pond bottom and top.
No, no. This elevation means which RL
This
RL of what?
this elevation shows the tank top and bottom level. If you see the profile,
Okay. Okay.
understand? Here we are giving some tank is coming like this now. So we are giving this bottom level and top level in that area.
Okay.
So that elevation only that is.
Okay. 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 Means above one is the bottom level and
Yes, yes, yes.
below one.
Below is the top.
Okay.
So in this table, whenever we are entering, it should be ascending order only. The value should be in the ascending order, elevation value.
Okay. Okay.
Okay. Huh?
Yes. Yes.
If you are giving 34.5, now we can see that one also. You can clearly understand 34. You are giving 32 means if you validate it, warning will be coming. See, error came. Like elevation area must be in the increasing. So it's showing because of that only we should be giving ascending order. 32, 34. Whatever point you needed, you can create like this here. So now if you run means no warning will be coming. Okay, understood now?
Yes. Yes. Yes.
So no warning is coming for that tank. So this warning is based on that computational time interval which we are given in the options. So if you reduce that, that will go this these timings. Okay. So another outfall is tidal. Next, boundary condition type. If you go to this tidal outfall, so these are the four outfalls which we use regularly in the stormwater design. So for the tidal outfall, if you are designing something like island kind of thing, so the water will be directly discharging into the ocean. So if the water level in that case, consider this as a ground. So this as sea. If your stormwater pipes comes and connect it here or something little bit above, so there will be some waves will be there in the for the tidal. So in that time we need to take that tidal wave and so for example this is one tidal wave. which I have created for example. So in that time we need to add in the boundary condition, so to make ensure that there will be no backflow effect and there will be no flooding also. So whenever the peak, whenever the wave reduces, some amount of water will be discharged from our network to the sea. Then whenever the flow discharge increases, in this place there will be no water; it will be stopped. So in that time we need to use that tidal. So in that time also they are given like a route to catchment. Like so there is some peak consider here this point. So our pipe is connecting like this. So in that time there will be some amount of water will be coming inside our pipe. Some flooding will be happening in that nearby catchment. So for that also we need to select the catchment and we need to select the table here. Time versus elevation of that wave. So if you go to this time and elevation, select, if you give copy and paste means that will be coming exactly which you are created or which you are getting from some other else. This is how we need to use this boundary condition. Okay, so if you are using this multiple boundary condition, we need to ensure that you are having separate boundary condition like swim. So because these structures and all won't run in this rational method. Okay, then okay, almost we have finished that. So the main thing I want to do is a small recap for the profiling. First we'll delete this. Go to rational. So we are going to do profiling. Close this catchment. First we'll see the profile. This is the full profile. Close this. So here we can see there is crown to crown matching here, but we are having a drop here and we are having a drop. So we can see some this profile is also okay, but as an engineer you can design like you can drop this to here. You are seeing my mouse, right? You can connect this and you can reduce the pipe little bit down. So how to reduce this? There are multiple ways to reduce this. First we will see the simple way. So this is what we have done in the last class itself, but this is more important, that's why I'm taking it again. Okay, so go to the manual 9. So this is the manual 9. Select this conduit. First we are not going to design anything in this because which is already designed. So what we are going to do is we are going to connect this pipe inward to this pipe inward. So this exactly this manual inward. Yes.
Yeah. You know why it is important to connect the pipe. You said this profile is okay, right?
Ah,
And how can identify whether it is okay or we have to connect?
okay. So if you see the profile, this is everything is about the designer perspective only. So if you can submit this also, this will also get approved and agreed. But if you see some, if you can able to, this is kind of a beautification only, beautification of profiles. We can simply tell. So there is multiple steps now. So here one drop, here one drop. So in the construction perspective, it will be quite difficult to construct this. So if you make a drop here means, so they will dig until here uh, for a slope of this area, and they will put the pipe and connect it directly to the manuals. Did you get Vinay?
But for yeah, I got that. But we will introduce the drop
Uh,
to reduce the flooding only, right?
so the drop,
Anyway,
yeah. Not only for that
then
purpose,
why we
not only for that reducing the purpose, to make the profile to visibly see, it is like looking if it is, if you see this profile, this is also looking good only, but here there is some drops, two drops are there, here one drop and here one drop. We can make one drop directly here and we can make a smooth profile here. So for that purpose we are doing. So making a drop is not only for reducing the flooding, it is to beautify the profile also. So to
Okay.
reduce the flooding, two things we can do. One we can do is like increase the pipe size. Second, we can introduce a drop, or we can reduce the pipe connecting cover.
Yeah,
Uh,
got it.
okay. So now what we are going to do is we are going to connect these two pipe little bit, making a drop here, and we are going to connect it to this manhole. Okay. First simple method is here we are going to do design anything. So go to this previous manual conduit 10, design the stop inward. So this is the stop inward of this pipe. Then go to set inward to start, set inward to stop, make it as true. So this will be connecting here. First we will reduce this pipe, then afterwards we will reduce this conduit 9, then run it. Some warnings are there. Selected runoff method, e-passing runoff method not supported, only rational method is supported. Go to scenario for this warning. Go to scenarios. They're telling like the runoff method of the catchment is selected as e-pass swim. Okay, so change to rational method. Set this runoff coefficient default. GVF rational only. Calculate design. Whenever you are running, we need to ensure that this is in design option and this is in GVF rational. So this is what I am seeing here. Then validate it. So that error gone. Go to profile. See, while changing this manual itself, this has automatically created the sewage gems itself automatically created a drop here. They have connected these two pipes in this bottom itself. This is one method, like making a one second, making the design invert as false and making the set invert to stop. Set invert stop need to be in true only. It is connected. So this method you can, where we can use is if you want to adjust one or two conduits or one or two manuals means we can adjust it, we can adjust in that way. Okay, this is one method. So then we go back to our normal. here we will be having a drop. Okay, so then one method we have seen. So this is where we can use this in the small portions, like one or two manuals, one or two conditions we can use in that way. So if you want to adjust everything to be like whole thing need to be a whole thing, we should have a drop like from the starting itself, means we need to play with the cover level. So go to this manual, manual 6 and the conduit 9, manual 6, so the conduit 9. So what we are going to do is we are going to adjust the cover level of this conduit, so it will automatically have a drop and it will connect it here. Okay, so make the specify local pipe constraint, which because we are going to change one thing, some things for that particular manual, it's a particular conduit. Set everything, pipe node, stop everything. Okay, so come here. So it's kind of a trial and error method only. If you know exact value, we can't find the exact value how much we need to drop, it's kind of trial and error. So go to cover minimum pipe constraint. Previously it was 1.2, now I will be giving 1.65. Just I'm just putting a trial. So we can we need to ensure that this manual need not to be changed, like manual 9 need not to be changed. So go to this, before running go to this design structure elevations false. So what I want is these two conduits need to be adjusted little bit down, but this manual need not to be designed, like it should not be like increase the depth, or it should not change the value. For that what we have done is we have changed the minimum cover level, and we have make a false of the design structure elevation of manual 9. So run it all. Okay, some amount of pipes has been make little bit down. This is not enough, so go to the same manual. Before that I need to check something, because it is coming like this pipe is structure on and off, everything is true only. Make sure if you are designing a rational, everything is as true. The design structure elevation, for this manual we need to adjust this. For this conduit, previously we have given 1.65, now what we are going to do is 2. Go to compute all. Actually some issue with this manual, because click this design, local pipe constraint matching, design structure elevation is in true only. Okay, so if you can see this, after making a 2 as a minimum cover, this has given a little bit down, so we can adjust little bit more to match the slope. So go to the same conduit, select this, instead of 2 I'm going to put 1.85. So now we almost matched it here. So if you can see here, some small amount of decision is there, so we need some more drop. By seeing this we can understand that we need some more drop. After manual 6, 1.85 is there, I am putting 1.9. It may match or may not match, we need to adjust it accordingly. So 1.9 is making too much drop here, so I'm going to adjust it into 1.88. So now it is perfectly matched. If you want to adjust little bit more also, we can match it here, because here we'll be having some amount of steep slope here. So slope is 600, this slope is 1044, and this slope is 1000. No issue. If you want to make a proper profile, some slope distortion will be there, in that we can adjust in that way. Okay, so the another method is kind of we can adjust it manually. If you want to adjust, if you want your pipe need to be fixed in some value, means we can do that also. So before that I will close this. It will come back to normal. So this is how it's happening, like smoothening the profile. Like two methods we have seen. The another method is like it's like a manual adjustment. That one I don't prefer, because it will take too much time. If you are good at Excel, it is good, but we don't get this proper sloping. Here you can see now this is 500, 700, 1000, 1000, 1000, 1000, 1000, 1000, 1000. If you do calculate with the manually, there will be some like 999 point something, or 1000 point something will be there. Some amount of slope will not be accurate. Okay, to get the proper slope, like rounded value 1000, the doing rational method will be good. So the third method is like adjusting to the manually. So after manual 9, so this is the manual 9. You can take the invert level of this, go to the previous manual, make the design stop, because we are going to connect it with the manual numbers. Go to design stop. No need to make it true, because we are giving our value, so it will automatically connect. This case we can do when your multiple junctions are coming, like pipe is normally flowing like this, but some pipe is coming will be coming like this, some pipe will be coming like this. In that case we can't directly connect, in the rare case we may not directly connect it like this. If you want to adjust it, we can connect it here. If you want to adjust it, we can connect it here. Based on the manual invert, we can connect whatever you want. Only thing is it want to flow upward. So in that time we can use that. So now we'll get this to normal. So go to this. So now what we have finished is how to set parameters for swim runoff method, then what are the outfall boundary conditions available and how to use that, then small recap of how to smoothen the profile. So this is the same thing what we have done in the yesterday's last class itself. So in the last class also we have done like how to do this profile smoothing and how to give parameters for SES runoff method. So that one also I have shown it here. So then I just want to show one more thing is how to introduce the pond and how to develop the structures. So these are the multiple things which is available in the COGEMS which we can use. So if you want to introduce a pond or tank, both will be same only. In the COGEMS, both will be same based on the levels which you are connecting will be different. So if you go to this, we can create a pond here like this. Okay, if you want to connect the catchment, go to the outfall, go to boundary element, select this outfall, this will be coming. Okay, next thing is I want to uh, take water from this pond. So how to connect? This will be like a temporary pond, detention pond. It will be a temporary pond. After 24 hours, I will be telling the logic only today. So based on this, will be the next tomorrow's class will be continued. Okay. So I want to connect. I want to take water from this pond. Means what we want to do is we need to introduce pond outfall structure. This will be available in the layout. Go to layout, connect pond outfall structure. So pond which will be creating elevation area, so which we have seen is 30, 200, 32, 200. So we have created a rectangular pond. From that we will be getting water from the system. After water coming into the pond, after 24 hours there will be a discharge from the outfall structure. Okay, go to this, select this outfall structure, put some elevation ground area which is available near to this, which is 36. Then select the upstream pond, non select the upstream pond. So as a control structure, like so this will be covering in the next class. So after this we can connect to some other manual or something. So the pipe will be connected like this. So the water will be coming from the system, will be transferred to the pond. After 24 hours it will be discharging to the manual. So this will be covering in the tomorrow session. Hello. Yes.
This pond and all outfall structures, pond, etc. We cannot model or design in the rational method, right?
Yes, because that
We
the
are
solver
choosing
which we are
we are
using in the
choosing
yes
we are choosing which solver and which method for this.
so the rational method it will be using GVF rational. Okay, so if you go to this GVF rational, uh, in the options we'll be using GVF raster, so it won't support the external structures like pond control sets like level control and time control. It won't support. So because of that, we'll be using
Right.
explicit solver in the swim runoff method or SCS runoff method. So in that solver, it will be supporting everything like control structures and all.
Okay.
So that's all for today. So tomorrow's class will be like how to yes.
Yes, Venu.
Uh,
Venu, what about that pumping? Uh, so,
Yeah, that will be covered tomorrow only.
okay. Okay.
Here we can see the pumping also like a layout, the pump. Like if your system
Yeah.
is coming.
That pressure junction.
Yes.
What is that pressure?
So I will tell the how it will be applied in the logic. Okay, if you are developing, consider this as This is our system. We are connecting to one pond here. Okay, pond or tank, consider this as tank. So water will be coming inside and it will be stored. So but the existing system is kind of it's coming in the little bit higher than this the tank level. Okay, the existing system is coming here, so one manual is coming here. So in that case we need to introduce one wet well here, so to install the pump. So water will be coming gravitationally to this area. After that we will be pumping these two here. So to use to use pump in the CHMs we will be using pressure pipes, HTP, that pipes will be using. So for that pump whenever we are installing the pump, next to the conduit will be there no. So in that case we will be using the pressure junction. So that will be covered in the tomorrow's class. Tomorrow's class will be about how to set up tank, pond, and outfall structures and these pressure pumps. Then go to these components. Yeah, SWMM extensions, control sets will be there. So this will be doing in the next class. Most all the control structures we can control it here itself, like putting some that small formulas. Okay. Okay, that's all for today. Any doubts from today's class?
No.
So Vishal sir, I have covered last class what we have taken also. So you understand right? Like how to get input parameters for SCS runoff method, how to do profiling,
Yeah. For HDS, we have to change only
that
uh,
runoff method and two
the
inputs.
catchment
Ah,
to okay.
ah,
Only the unit hydrograph,
yes,
right?
yes,
Only that is the
yes,
change.
yes.
And we have to give some CN number.
CN, yeah, for unit hydrograph method, two inputs. One is CN, one is time of concentration. So today,
Time of concentration in 10
10
minutes.
minutes, yes, that is based on
And
standards.
CN number is 75 or it depends,
Depends
right?
on plots.
Whether it
Uh,
is on the slots.
okay.
Okay. So more the number means it is more impervious. Correct?
No. More the number in CN means it will be more runoff will be coming from that area. So
Yeah, that is what is more
yes,
impervious.
yes.
Mm.
Ah,
Venu, I can't access that videos you shared, that YouTube videos.
okay. You send your mail ID to me. I will add it to you.
Okay.
So when we are converting the rational to dynamic method, like SCS or swim, we need to ensure that we'll be creating this multiple options in the alternate in the scenarios. Like for the active topology, we need to create a separate thing for SCS and swim. For the boundary condition, we need to create SCS and swim because in the boundary condition which we are using in the swim, we'll be adding tanks and something else, but it won't the same run in the rational method. Because of that only we are creating a different boundary condition. Okay. For the hydrology, we need to create a separate thing because hydrology depends totally on the catchment parameters. For the rational, we'll be giving different catchment parameters. For the swim and SCS, we'll be giving different catchment parameters. So this thing need to be changed. Active topology, boundary condition, hydrology, rainfall runoff. So this is the four main thing we need to change when we are converting the same rational model to the SCS or swim dynamic model. Okay. Any doubts, Surya?
No.
Okay. Okay. Thank you all. Understand? Everyone understand, guys? Praveen, Akshata, Sweta. Okay, guys. Thank you, guys. We'll see you tomorrow.